Welcome back. In this session, we are going to continue the differential protection of a transformer. Last time, we stopped at the differential current. During our last session, we said that operation ID is the differential current must be bigger or equal to K multiplied by IR. The restraint current and the slope of the differential characteristics. Now, K is known as the slope. It's known as the slope of the percentage differential characteristic. IR is the actual restraint current, and IR from the previous lecture it's equal to I of CT1 plus I of CT2 over 2. Let's first discuss K. What's K? K, in a typical value for K is expressed in percentage, and a typical value with a typical value of either 10%, 20%, 40%. These are the typical value for K, the slope of the percentage differential characteristics. It's worth noting we should be able to see if you have a relay with 10% slope, it will be way more sensitive than a relay having 40% slope. Let's put the graph for the errors. I want to represent IR, and this is ID for the differential. The first error, in this one, I have the mismatch error. Mismatch error. The mismatch error is related to the mismatch between the windings. Remember from the previous lecture, N1 small and N primary equal to N2 N secondary. The second error will be known as CT, and then you will have ULTC. ULTC stands for under load tap changer. That's under load tap changer, and then you will have margin. This will be your trip zone. So K is defined by this. That's what defines the slope, the percentage slope, the slope percentage of the differential characteristic. I hope that's clear. The best way to see how can we calculate the mismatch error, the ULTC and the CT error, is by taking an example. Let's take an example and see how can we relate all this in a real protection case study for a single phase transformer. I want to consider a single phase transformer with the following data. I have a single phase transformer. I have 69 kilovolt, 110 kilovolt transformer. The system has a 20 MVA power. The system has a under load depth changer of 5%. What does this mean, under load depth changer? That means the changing of the windings can vary by 5%. Can vary by 5% under load depth changer, the depth of the actual winding within the transformer. One more element we have to pay attention when we choose a relay. For the relay, every relay has a tap, current tap. What does this mean? To make sure to minimize the error, every relay will have a tap to connect the actual output of the CT. In these conditions, we are going to use a relay with the following taps. So I have a relay with the following taps: 3 amps, 4 amps, 4.5, 4.8, 5, 5.1, 5.2 amps. So whenever you obtain a relay, the relay has an options of these steps. Why we choose this step? You will see now, part of the question, you will see how to use these steps. Now, question number 1, I need to specify the CTs. Question number 1, I need to specify the CT for this protection. How do I specify the CT of this protection? Let's have a look. I need 2 CTs. I need CT1 and I need CT2. That's what I need to protect the system, to use the differential percentage differential relay. Let's see now, how can I determine the characteristic of these CTs, the specifications. Number 1, I need to determine the primary current, and then I need to determine the secondary current. The determination of the primary current and the secondary current will be based on the actual transformer rated system. Let me try this circuit analysis. What do I have? It's a single phase transformer. So I can apply straight away, I can say S is equal to V I conjugate. I'm interested into the magnitude of the current. So I primary will be equal to S, which is 20 10 to the 6 divided by 69 10 to the 3 is equal to, and the secondary current will be equal to 20 10 to the 6 divided by 110 10 to the 3. So the primary current will be 289.85 amps, and the secondary current will be 181.8 amps. From our CT chapter, what can we determine now? It's clearly shown that for the primary, for CT1, I need CT ratio of a 300 to 5. And for the secondary, I need 200 to 5. If you have any information, how do we obtain the 300 to 5, 200 to 5, please revise the CT chapter. Let's take a moment to digest this information. To go one more time. Number 1, to determine the CT specification, I need to determine the CT ratio. The most important element when I determine the CT ratio is I need the primary current and the secondary current. I need the current that goes into the CT. How do I determine this? By using the power equations. The complex power is equal to VI conjugate. I am interested in, at this stage, because single phase, I'm interested in the magnitude. This magnitude, I find the magnitude of the primary current and I find the magnitude of the secondary current. Both magnitudes will lead for me to determine, to specify the actual CT ratio, 300 to 5, 300 to 5, which means under perfect condition, this current and this current, they will never exceed the 5 amps under rated condition. Only will happen, it will exceed it under fault condition. I hope that's a very clear. Now, the next step is I need to determine the error. Like I said, the error, I need to determine K. To determine the operation condition, I need to determine K. Is K 10%, 20%, 40%? Let's go step by step. Number one, I need to find the mismatch error. The mismatch error is related to the actual number of windings. Now, in order for me to determine the mismatch error, I need to find the actual secondary current of CT1 and the actual secondary current of CT2. So now I know, let me write this so I can delete the bottom. That's a 300 to 5 CT, that's a 200 to 5 CT. This IP is 289 amps. Isn't that what we found it to be? 289.85. And this current is 181.8. So the primary current of CT1 is 289.85. So therefore, I secondary of CT1 will be equal to 289.85 multiplied by 5 divided by 300. The answer will be 4.83 amps. On the secondary side, I have a secondary for CT2 will be equal to 181.8 multiplied by 5 divided by 200, and the answer will be 4.54 amps. Now, in this number, I need to find the relay taps. The closest relay tap will allow me to reduce my error. As you can see, if the relay has only one tap of 5 amps, and this you have to go back to the relay chapter to go more in details in relation to the tap. Inside the relay, there's an electronic circuit. If I have only 5 amps, can you see the difference between 4.83 to 5? There's 0.17 amp different. However, if I choose the 4.8 tap, that means I have only small error, which is 0.03 amps. That's why every relay will have a multiple option of taps to reduce the error. Same for this one. For the secondary, I have 4.54 amps. If I only have 5 amp tap, what's going to happen? I will have an error of 0.46 amp. However, now I can use the 4.5 tap, which will reduce my error to 0.04. So let's see what sort of error I'm going to get. All I have to do now, I have to divide this by this. For the primary, I will have 4.83 divided by 4.8. On the secondary, 4.54 divided by 4.5. This answer will be 1.0063. This answer 1.009. Can you see the advantage of using a relay with the multiple tap options? This way I reduce my error. That's number one. Number two, what can I do now is inside the differential relay, I'm taking this current and I'm actually minusing. Remember ID is equal, I of CT1 minus I of CT2. So therefore now, the error, if I go ahead and I minus these two, will give me an error of 0.3%. As you can see, 1.009 minus 1.006 will give me 0.003, which is give me 0.3% error. So if I go back, let me delete this. I want to draw this back. This is IR, this is ID. The first error, the mismatch, was 0.3%. The second error is, the second error that we discussed was the CT error. Now, two options. Either we will have the input data to calculate the CT error as we've done in the previous chapters, or we will go into the data sheet as we did in the previous homework. We go to a data sheet and we will find a CT with a nominated error, and we say this is the error, this is the CT type that we're using, this brand, and this is the error. Or for the sake of this example, I want to say it is 10%. For the sake of this example, I just want to say 10%. You will have, the next one is the ULTC, which is 5%, it's given. It's telling you that you can change up or down by 5%, plus or minus 5%, which means I have 5% error. The total errors now for this one is, if I add all of them together, this will give me 15.3%. 15.3%. What we discussed before regarding to K, it is a 10 typical value, 10, 20, 40. So I use a 20% K in this case. So my system now K, it's equal to 20%. This will give me a margin. This will give me a margin of, from 20 to 15.3, 4.7% margin. And that's very, very acceptable in our system. That's why I would choose a margin of 20% when I do my relay settings. Is that clear? How do I choose a CT? How do I calculate the error? And this now will be my trip zone. And in the previous video or the previous lecture, we discussed the element, what's the differential ID, what's IR, and so on. In this, I'm hoping that this example gave you enough information regarding determination of the CT ratio, and then determination of the actual CT mismatch error, CT error, which is already done it before, ULTC in the margin, and how to specify. So now I can say I need a CT on the primary side of 300 to 5, on the secondary side 200 to 5, and then I will say that I need a relay. I need a relay connect the primary on for the depth 4.8, the secondary 4.5, and then I have a relay of an error of K. The slope is 20%. I hope that's clear enough. Now let's do some more example as a practice together.